Hey folks, I got an example using Newton synthesis. If you need a moment to pause the video and copy down the data and the diagram, please do so now. All right, let me explain what's going on here. So we got an unidentified planet here that you're going to go into orbit around. And the planet has a radius of about 6,000 kilometers, which is very similar to Earth. If you're in your circular orbit, it takes your spacecraft 3 hours to orbit in a circular orbit, and the height of your spacecraft is 2,000 kilometers above the surface of the planet. I want you to determine the acceleration of gravity, little g, at the surface of the planet using this data. Now, two hints. One, these are in kilometers, so you need to make them in meters. So you're multiplying both by 1,000. Okay, so it's 6 million meters and 2 million meters, respectively. And actually try this out before you watch my explanation, and then see if you match my explanation. Are you ready to try it out? On your marks, get set, go. All right. Now pause the video and try it out yourself for real. Go ahead, pause the video. Go ahead, do it. All right. Hopefully you've tried this out on your own, but I will now walk you through the explanation. Okay. So I'm going to give you the answer. The answer, little g at the surface of the planet, is approximately 4.81 meters per second per second. So by the way, if you just got that on your own, awesome. Okay. If you didn't, we'll see if you made a simple boo-boo somewhere that you can fix. Okay. So in order to find little g, okay, I'm going to use big G, mass of the planet, over radius of the planet squared. Now, I want g at the surface. So this number here is going to be my 6 million meters. Okay, not 8 million, 6 million. I want to know what's little g at the surface of the planet if I'm standing on it. Okay. Now, in order to find this or determine this, I got to know the mass of the planet. Well, that's where I'm going to use Newton synthesis with the orbital data. So if I use Newton synthesis, which is this thing here, and I solve it for m, the mass of the thing I'm orbiting, okay, I get the following equation. So the mass of the thing I'm orbiting is going to be 4 pi squared r cubed over gt squared. Now, g is 6.67, e negative 11. By now, you hopefully have that programmed in your calculator. For r, in this case, well, we need the radius of the circular orbit that the spacecraft is making. Well, that is 6,000 plus 2,000 or 8,000 kilometers or 8 million meters. So for r, in this case, you'd have to use 8 million. Okay, that's the orbit we're making. For time, we said 3 hours. Okay, but we need that to be in seconds here. So there are 3,600 seconds in 1 hour. And if you take 3 times 3,600, you get 10,800 seconds. Okay, so if you plug this in for R and this in for T and do all that stuff there, you're going to get the mass of the planet. When I did this, I got 2.60 times 10 to the 24th kilograms. So now, by the way, Earth is about 6 times 10 to the 24th. So this is a less dense planet than Earth. It's about the same size, but less than half the mass. Okay. And then you use your little g equation. G equals big G times the mass of the planet, which is that. And then here's where you're going to plug in your radius of the planet itself, which is 6 million meters squared. And if you do that, you get the answer I laid out earlier, which is your 4.81 times 10, or 4.81 meters per second. So by the way, if you were to land on this planet and get out and walk around, you would feel about less than half your weight. 4.8 is less than 9.8. So like for me, I weigh about 180 pounds. On this planet, I'd weigh something like, I don't know, 85 pounds or so. So I'd feel real light. I'd be able to jump significantly higher, and it'd be kind of fun. So I hope that example was helpful, and thank you very much.